Hello everyone, my name is Muhammad Zaki Naufal. Today I would like to present the review on paper with title Predictive Deconvolution Method for Non-White Noise Reflectivity. This will be my outline through my presentation. So I would like to start with the abstract of the paper. The conventional predictive deconvolution assumes that the reflection coefficients of the Earth correspond to an uncorrelated white noise sequence. However, in the real data, the primary reflectivity series of data rarely satisfy with noise sequence assumption. So with that, this paper is proposed to improve method for the convolution that can adapt with non-white reflectivity series without changing the statistical characteristics of primary reflection coefficient series. Next, I would like to explain a bit on predictive deconvolution. Predictive deconvolution is a crucial step in the processing of seismic data, and it plays an important role in enhancing seismic resolution and multiples attenuation. This method generally uses the least squares algorithm to solve the predictive filter and eliminate the predictable parts of a seismic record. However, over the past few decades, examination of logging data has shown that primary reflection coefficient sequence is best represented as non-white noise, or in this case, as a blue noise, compared to the white noise. And this blue noise has non-Gaussian and fractal features which are similar to the output of a chaotic generator. So these are the traditional predictive deconvolution processes. So I would start to explain from the beginning that the first is a noise-free seismic record can be represented by a convolutive model with these equations, where dt represents a seismic record, wt represents the wavelet, and ct represents the Earth's reflection coefficient sequence. And assuming that the wavelet is in minimum phase, we can calculate the predictive filter operator to eliminate the predictable parts of seismic record under the condition of minimum prediction error energy by using this second equation. And after that, where m represents the prediction step, this equation can be solved by using the Wienerhoff equations. As you can see here, the n variable represents the length of the convolution operator, where the matrix consisting of the RT on the left side of equation is known as the Toeplitz matrix. Once the prediction operator Ft is obtained by solving equation of Wienerhoff, then the output of predictive deconvolution can be obtained by using these OT equations, where OT represents the output of predictive deconvolution. Then, where Tm represents a delayed time of multiples, including the first order multiple and higher order multiples occurrence after the primary reflections, that we can combining these OT equations and with combining with the convolutive model become these RDT equations. And with the assumption of the primary reflection coefficients are uncorrelated, then if there are multiples and primary reflection coefficients conform to white noise series, the equations of autocorrelation become these RCT equations. And by substituting the previous equations, the autocorrelation become these new RDT equations. So that's how the traditional predictive deconvolution process. Now this paper is trying to apply the new method that can adapt to non-white reflectivity series as explained earlier. And also this paper is trying to reduce the processing noise and improves the accuracy of the result itself. However, these objectives of paper is come with the current issues. With the first one is based on the general assumption that I've explained earlier, that traditional predictive deconvolution method can only recover the white parts of reflection coefficient sequence. And the second one, the examination of logging data has shown the primary reflection coefficient sequence is more related to non-white noise compared to white noise itself. This blue noise or non-white noise has a similar features to chaotic generator. So with that, this paper is trying to propose the improved predictive deconvolution. The first step is to use the spectrum modeling method by using this general equation for autocorrelation with non-white primary reflection coefficient sequence. However, the autocorrelation of seismic records, as you can see in this equation, there are three parts. The wavelet autocorrelation, the correlated components caused by existence of multiples, and other correlated components. However, the other variable represents the other correlated components, which mainly includes the correlated energy of primary reflection coefficient series and the non-orthogonal parts of primary reflection coefficient and the multiple reflection coefficients. So after predictive deconvolution, the corresponding energy of R other T is also predicted and eliminated. So to fit the amplitude spectrum under minimum error energy, this WF equations is generated with alpha represents a constant and F represents the frequency and WF represents the spectrum of seismic wavelet. The wavelet amplitude spectrum was expressed by these equations, the HF, where WF absolute value, this can be used to fit the amplitude spectrum under this minimum error energy. Then by fitting the amplitude spectrum of seismic records, we can determine the values for K0, K1, and K2 in the HF equations, and then to calculate the value of absolute WF variable. And then the wavelet autocorrelation estimation become these RWT equations with the inverse Fourier transform of the absolute value of F square. And then this new autocorrelation function that consists of two parts, the RWT and RMT, is generated. That this RET represents the new autocorrelation that needs to be solved, and RWT can be obtained by solving the previous equations. And after that, we transform the convolutive model into frequency domain with these equations. D equals to W times by R. This DF represents the spectrum of seismic records and R represents the spectrum of reflection coefficient sequence. The RCT variable was obtained by calculating the inverse Fourier transform as shown in the equations below. And if the reflection coefficient sequence is non-white and without multiples, variable R empty becomes 0, and the autocorrelation equations become this equation RET equals to A RWT. Then from the previous improved method, it can be combined with the Wiener-Hopf equations become these equations, where RET was obtained by our improved method given an operator length n and prediction step of m. And after the solving the previous equations, this OET become the new output of the improve of predictive deconvolution for non-white reflection coefficient sequence. So these are the result was taken from the modeling. So the top one is the comparison of result of bandpass filtering after zero phase deconvolution with length of deconvolution operator is 160 milliseconds. With the left side, the A is the theoretical result, and then the middle one or B is the traditional method, and the C is the improved method. As you can see here in the traditional, we still can see the noise at the end. However, in the C, the improved method, the noise at the end can be reduced. And then the bottom one is the comparison of similarity coefficients between theoretical value and multiple attenuation result using different predictive deconvolution method with prediction step of 100 milliseconds. So these are the results from the field data difference from the previous by using the model. This is the result from the field data. So the top left is the comparison of results from traditional method and improved method. The traditional one is on the left and the improved method is on the right, with the length of the convolution operator is 2000 millisecond and 100 millisecond prediction steps. And as you can see here, once again, the improved method can be delineate the noise here. And also same it goes with the bottom one. This is the comparison of similarity coefficient between theoretical value and multiples attenuation results by using different predictive deconvolution methods. As you can see, the A is the traditional one and the B is the improved method. Then it shows that the improved predictive deconvolution it generate the better result compared to the traditional one. So the conclusion is that the improved predictive deconvolution method can adapt to both white and non-white reflection coefficient sequences, and this method can preserve statistical characteristic of primary reflection coefficient while attenuating multiples. And last but not least, this improved predictive deconvolution can improve the seismic resolution, reduce the processing noise, and improve overall accuracy of the results. Then these are my references for the review paper. Then with that, I would like to end my presentation. Thank you for your attention.